Alright, this is the problem we started working on in class the other day. It's number 31. It describes a monatomic ideal gas and a number of processes that it undergoes. And the first part of the problem is to sketch it on a PV diagram. So we'll sketch that here, right? We have on a PV diagram, it starts off at some initial pressure. I can't remember what that is called. Oh, the initial pressure, P1 is 1 atmosphere. Sorry, so let's draw that down here somewhere. 1 atmosphere, and P2 is 2 atmospheres, and it goes up to P2, expands at constant pressure, the gas is heated at a constant volume to a pressure of 2 atmospheres, and then expands at constant pressure until it's 49.2 liters, so it goes off something like this. And then is cooled at constant volume and then decreases in volume that away. So you can see this is 24.6, I think, liters here, and this was 40 something, 49.2, right? It's double. It's 49.2 liters. That's just double. This is double what this is. This is double what that is. That might actually be really useful for us. It has to draw the PV diagram. Whoopah! We're done, right? PV diagram. Sweet. We actually did this part in class. And then for each step, calculate the work done by the gas. For each step of the cycle, calculate the work done by the gas, the heat absorbed by the gas, and the change in the internal energy of the gas. We can look at this and say something about the total change in work and the total change in internal energy qualitatively by simply noting this is going around in this direction, this is a cycle. Each of these processes, the work done is the area under the curve for each of these steps. And so for the whole net process, the area underneath this curve is going to be equal to this area right here. And the change in internal energy for the entire thing is going to have to be equal to 0, right? So because it starts here and it ends here. So the change in internal energy is simply equal to the final internal energy minus the initial internal energy. So we know that the whole thing is going to be 0 around the entire cycle, and the net work needs to be positive. The net work done by the gas, that is. Net work done by the gas is going to be positive. The net work done on the gas in this case is negative. So cool. Oh, we're going to find the work done, for the work done by the gas. So that's just kind of a nice thing to pay attention to. We want to know what the work is being done by the gas for each of these different steps. And we talked about this in class, how the work done by these two steps is going to be 0. There has to be some type of displacement while there's a force acting on it. And so the work done here in this process, let's actually give these some labels here, right? Let's say A, B, C, and D. So the work from A to B is going to be equal to 0. The work from C to D is also going to be 0, right? There's no change in volume. There may be pressure here. There's definitely pressure. That's decreasing. But there's always going to be some positive pressure, but there's no change in volume during this time. We can also evaluate for each of this case, for the two cases here, the isobaric processes, we can evaluate the integral of the work done by the gas as being equal to the integral of PdV. Okay? For a isobaric process, this P is constant. Isobaric means constant pressure. So P isn't changing with respect to V. So we can rewrite this as simply being the integral of dV from some initial volume to some final volume. And that's going to depend on which direction we're going. Here the final volume is the volume 49.2 liters, and the initial volume is 24.6 liters, and our pressure is 2 atmospheres. So we can plug this in. The work done from B to C is going to be equal to the P2, the pressure of 2 atmospheres, times the change in volume, which is going to be this V2 minus V1, where V2 is equal to 49.2 and V1 is equal to 24.6. Right? The work done by the gas from D to A is going to be P1, the pressure down here, times the change in volume. Well, the change in volume here is going to be the final volume, V1, minus V2. Where V2 is going to be the larger value of 49.2, so this is going to give us negative work, which is what we'd expect. The area underneath this curve will be negative because it's going from, integrating this part is going from this piece back to here. So we get negative, this is positive, this one's going to be larger, and that's why we have a network being positive here. Right? I'm going to stop this one and start it up again.